So again, we will start. In the previous lecture, we already learned about why this transition metal shows color. So these are the parameters required for the color of the transition metals. First one is if the unpaired d electron is there, it will show color. If it shows the dd transition, again it will be colored. And if the ligands are changed and then the geometry of the complex is changed, the color will be changed. So we are discussing this example of cobalt chloride. See, if this cobalt chloride, it is also available in our laboratory. After this COVID situation, we can do this experiment in our laboratory also. If this cobalt chloride is dissolved in water, the pink color solution is formed. See. And why this pink color solution is formed? Because the complex is different and its geometry is also different. If you see carefully, such type of complex is formed, COH2O6 2+. Means the ligands are, water ligands are there and it is having the octahedral geometry. And if the same cobalt chloride, if it is dissolved in concentrated HCl, remember, the blue colored solution is prepared. Blue colored solution is prepared, and this is this complex is prepared COCl4 2-. See, A6 ligands are there, and there are 4 chlorine ligands are there, and these, see, the geometry of the complex is tetrahedral geometry. When this solution, when this cobalt chloride is dissolved in water, it shows pink solution, and this pink solution, in this pink solution, if the concentrated HCl is added, this complex is formed, COCl4 2-. So the reaction is shown here. So this is a pink color solution, and we are adding concentrated HCl. The geometry is also changed and the color is also changed. The color becomes blue. Means we can conclude that when the ligands attach to the central metal atom, the nature of the ligands is changed, the color will be also the change. Then if the geometry of the complex is changed, here it is octahedral geometry. In the first case, the geometry is octahedral. In the second case, the geometry is tetrahedral. So if the geometry of the complex is also changed, the color will also change. Means colors depends upon not one factor, it depends upon many things. So in this diagram, we can see there are different colors are shown. Color of the some first row and transition metals are shown from scandium to zinc. So from this left to right, first one, this is a vanadium V4+. So this is the color of the V4+. This is a vanadium 3+. This is a Mn2+. This is a iron 3+, Fe3+. This is a cobalt 2+. This is a nickel 2+, and this is a copper 2+. This is shown for your understanding purpose. If the unpaired electrons are changed, how the colors are changed. So for the examination purpose, this is not expected to remember the colors, which color for which cation, but only we have to remember these points. Except these 4 points, one important point is there. Color of the transition metal due to the charge transfer. Means if the charge is transferred from one element to another element, the color is also there. So we know the famous example is there. This is not as for the examination, but this is for knowledge purpose I am giving. This content is not for your examination. Which examination? For board examination. This is for only competitive examination, for the CET purpose and for the NEET purpose and for the JEE purpose. Those students who are appearing for this competitive examination. This content is not for your board examination. Remember, once again I am repeating, the color of the complex, this is for knowledge purpose I am giving this example. KMnO4, this is a purple colored complex we are using for last year in 11th standard also. We are using this KMnO4 for titration. We already used, it is intense purple color. That's why this particular part I have shown with purple color. This is a purple colored intense purple color solution is there, and the reason behind this why KMnO4 is purple color. If this question is asked for the competitive exams and they will give the different options, for example DD transition, they will give the absence the presence of unpaired d electron, they will give the option geometry of the complex, and they will give the charge transfer. So remember the answer is charge transfer. So I will explain how the charge is transferred from this MnO4. So in this case, MnO4 minus is an intense purple color solution due to the charge transfer. So how the charge is transferred in case of this MnO4 minus, an electron is transferred from oxygen to metal. Means charge from this oxygen, it is transferred to manganese. See. So the charge of this charge of oxygen will be changed. It will be O22 minus 2O minus. So one electron from this O4, you know the oxidation state of oxygen is always -2. So the oxidation state of this oxygen will be changed. So one electron, if it is transferred to manganese, so the oxidation state of oxygen will be changed. Thus it will be changed O2 minus to O minus, and reducing the oxidation state of metal from +7 to +6, because one electron it is transferred from oxygen to manganese, remember, and due to this charge transfer the purple colored is appear. So during this charge transfer requires that the energy levels of the two different atoms involved are fairly close. So the energy levels of the oxygen and the energy levels of this manganese, these are very closer, so the charge can be transferred, remember. And there are also some compounds which are colored due to this charge transfer. One is Cr2O72 minus, CrO42 minus, MnO4 minus is this example is given. Then one complex, this is a nickel DMG complex. DMG, it is the dimethyl glyoxime. This is this DMG we are using in one test for the practical. Dimethyl glyoxime we are using for the detection of nitrate NO3 minus for the when detection of acidic radical, we are using this DMG complex, remember. So this nickel DMG, it is colored due to the charge transfer. So this is not for your board examination. This is for additional knowledge I am giving. This factor is also responsible for color. Remember, charge transfer, in which charge is transferred from one element to another element. And this is possible when the energy levels of these two different oxygen atom and this manganese atoms are very close. Then and then this charge will be transferred. Then I am coming to this catalytic properties. The D block elements having some catalytic properties. You know the catalyst. What is meant by catalyst? A catalyst is a substance which increases the rate of reactions. So most of the transition metals shows the catalytic properties. They also having the proven the homogeneous and heterolysis catalysis. Homogeneous means the reactant and the catalyst are in the same phase. Heterogeneous catalyst means the reactant and the catalyst are in different phase. If both are solid, it is homogeneous. If one is liquid and one is solid, it becomes heterogeneous. In 11th standard, we already learned about this homogeneous and heterogeneous catalyst. So these D block elements plays very important role in this catalysis. Directly I am coming to the examinations, examples. Which catalysts are used for the different reactions. First one is MnO2. This manganese dioxide, it is used as a catalyst, in which manganese, it is from the transition elements, remember. So this manganese, it is used for the decomposition of KClO3 to O2. For this reaction, this is used as a catalyst, decomposition of potassium chlorate to the oxygen. Then another example is this MO, molybdenum and iron. This is used for the manufacturing of ammonia by Haber's process. Remember, these examples are asked for examination, board examination. So they 100% the question will be asked for the examination if it is not asked for this exam, but for the board examination the question will be there, and for the CET also, for the JE also, the question will be asked on this part. So remember these examples carefully, which catalyst is used for which reaction. Then COTH, it is alloy of cobalt and Thium is thorium. This is used for the synthesis of gasoline. The synthesis of gasoline in Fischer-Tropsch process. Fischer-Tropsch process, it is the synthesis of petrol. In this process, this alloy is used as a catalyst, remember. Then nickel, you know this nickel, many times you already use this nickel as a catalyst. In 11th standard also use nickel. Finely divided or finely granulated nickel, it is used for the hydrogenation reaction, for the conversion of ethene to ethane. I mean, double bond is converted into the single bond, hydrogenation reaction. Ranni nickel, it is used as a catalyst, remember. So the H2 platinum is also used, but this is not in this platinum. Just wait, we will see it is in which block. We will see the periodic table. Palladium, platinum, these are also used for the hydrogenation reactions. But the Ranni nickel, nickel is present in D block elements. Yes, platinum is also in D block element. So we can write the example of this platinum also, palladium also, this nickel also. So nickel, platinum, palladium, these are used for catalyst for hydrogenation reactions. Remember, hydrogenation means addition of hydrogen, conversion of ethene into ethane. So we can write any one example of this. If the question is asked, write the catalyst used for write the different catalysts used for different reactions from this D block element. So we can give this example of nickel also. We can give the example of this palladium also. We can give the example of this platinum also. These are used for hydrogenation purpose. Then I am again coming to the catalytic properties. Many elements in this D block elements are, most of the elements are used as a catalyst. So the nickel is used for the conversion of ethene to ethane. Also, it is used for the conversion of inedible oils to the solid fat. This is called as production of margarine, remember. Means the hydrogenation process is carried out in which oils are converted into fats, but these are the inedible oil. We can't eat these oils. So this hydrogenation of oils, it is converted into solid fat. It is called as margarine. So remember this word for the examination. They can ask for the margarine preparation, which catalyst is used. So remember this name, nickel. It is used as a catalyst for this preparation of margarine. Then this is a Fe and chromium. These are used for the formation of CO2 and H2 from carbon monoxide and steam. Fe3, it is used for the catalyst for the reaction between iodine and persulfate ions. Then this is a platinized asbestos. It is used for the production of H2SO4 by contact process. In the chapter already I explained the contact process in previous chapter. The chapter was group 16, elements of group 16, 17 and 18. This contact process is used for the preparation of H2SO4. So in this process, there is one step, conversion of oleum, that is H2SO7 to H2SO4. In the last step, this is used as a catalyst, that is platinized asbestos. Then this Fe and this chromium alloy, this is used for the formation of CO2 and H2. Sorry, this is repeated. This is already taken here. Fe and chromium, it is used for formation of CO2 and H2 from carbon monoxide and steam. So remember these examples. These examples can be asked for the examination. Which catalyst is used for which reactions? Or they can ask for 1 mark, write the name of the catalyst used for, write the name of the catalyst of transition elements used for different reactions. Write any 2 examples. So remember any 2-3 examples which are important for the examination. Then the formation of interstitial compounds. What is meant by interstitial compounds? I will explain the definition first. The interstitial compounds are those compounds which are formed by when the small atoms like hydrogen, carbon, nitrogen, these are trapped. Remember, these are trapped inside the crystal lattice of these metals. So interstitial compounds means only the physical trapping is there. Bonding is not there actually. Only the trapping is there. Only trapping means these are trapped inside the interstitial spaces of the crystal lattice when the metal is formed, or the when the this is actually defects. These are the defects in transition elements. So the defects means these compounds like hydrogen, carbon, nitrogen, these are trapped inside the interstitial spaces. And this process is done when the crystals are formed. So the definition is also important. What is meant by interstitial compounds? So remember the definition. Some sulfides and oxides are also trapped, remember. So hydrogen can be trapped, carbon dioxide can carbon dioxide can be trapped, then nitrogen, not carbon dioxide, sorry, only carbon, hydrogen, carbon, nitrogen, these are trapped. Also sulfides and oxides are also trapped during the formation of crystals. So the some examples are given. These are the some interstitial compounds are given. So these are they cannot be represented by the definite composition, remember, and neither typically ionic or nor covalent. These are typically non-ionic because these are only the physical trapping is there. There is no any bonding. So this is a titanium carbon. This is one interstitial compound. This is a manganese and nitrogen. This is iron and hydrogen. So for the understanding purpose, only these examples are given. So these are the some examples of, in this carbon is trapped in the titanium lattice. In this nitrogen is trapped in the manganese lattice, and in this hydrogen is trapped in the iron lattice. During the crystals are formed. So there are some properties of these interstitial compounds. These compounds having the variable composition, hence do not have any normal oxidation state of the metals. Also, as the vacant spaces in the lattice of these metals are filled up, they provide them the new properties. When this carbon, nitrogen, and hydrogen or sulfides or oxides, when these are trapped inside the lattice, the properties of these interstitial compounds will be changed. One example is given. Steel and cast iron, these are the examples of interstitial compounds of iron and carbon, remember. Steel and cast iron, these are the examples of interstitial compound of steel is example of iron, and cast iron, these are the sorry, steel and cast iron, these are the examples of interstitial compounds of iron and carbon, means in which the carbon is trapped inside the iron. So due to the presence of carbon, here explanation is given. Due to the presence of carbon, the malleability, ductility of the iron is reduced. So to form a wire, to form a, what we can say, tin, means plane surface, malleability and ductility of this iron will be reduced, while its tenacity increases, toughness will be increased when this carbon is added. High carbon steel, it is also called as high carbon steel. So this property increases, tenacity increases, but the malleability and ductility decreases when carbon is trapped inside the iron. So this is one example of interstitial compound. Then I am coming to the properties. These are some properties of the interstitial compounds. First one, their chemical properties are similar to the parent metal. Means the chemical properties are same. The interstitial compounds are hard, good conductor of heat and electricity because they shows the properties of metals. Their melting and boiling point higher than the pure metals because their melting and boiling points are higher than the pure metals because there is a bonding between metal and non-metal, remember. When the metal and non-metal bonding is there, these bonds are very strong than the metal-metal bonds. That's why the melting and boiling points of the interstitial compounds are higher than the pure metals, because in case of pure metals, the bonding is between metal-metal, and in case of interstitial compounds, the bonding is between metal and non-metal. So these bonds are very strong. That's why melting and boiling point will be higher. Then their densities are less than the parent metal. Remember, these density of these interstitial compounds are less than the parent metal. Then hydrides of transition metals are used as a powerful reducing agents. Hydrides of transition metals are used as a powerful reducing agent. Hydrides, you know, these hydrides are the compounds with hydrogen. Then the metallic carbides are chemically inert and extremely hard as a diamond. This is a very important property of the interstitial compound. The metallic carbides, remember, these are chemically inert and these are extremely hard as a diamond. So hardness is also increases in case of carbides. Then I'm coming to the formation of alloys. We are familiar with this word alloys. Regarding the board examination, one question is always asked regarding the alloy. They will not ask the formation of alloys, but they can ask the short note. Write a short note on ferrous alloys and non-ferrous alloys. First, I will explain what is mean by alloy. Alloy, it is one metal is distributed randomly in the lattice of another metal. Means this is alloy is a combination of two or more metals. So in chemistry, We have to write the definition like this. One metal distributed randomly in the lattice of another metal. It is called as alloy, remember. It is a combination of two or more than two metals. It is called as alloy. So the alloys are formed when the metals with similar radii, means the atomic radii or the ionic radii are same, and then this alloy is possible. There are two types of alloys. One is ferrous alloy and one is non-ferrous alloy. The ferrous alloy means the percentage of iron is more. It is called as ferrous alloys. And non-ferrous alloys means the percentage of iron is less in this. So I will explain first this ferrous alloys. The ferrous alloys have the atoms of other elements distributed randomly in the atoms of iron, because iron percentage of iron is more. These are called as ferrous alloys. For example, it is given nickel, nickel steel, chromium steel, then stainless steel. These are the ferrous alloys in which the percentage of iron is more, then the percentage of nickel is less, then the percentage of chromium is less. So these are the some examples of ferrous alloys in which iron and nickel, this Fe nickel, Fe chromium, then this stainless steel in which iron is there, carbon is there. Mm, 2, 3 metals are there. It is called as stainless steel. All steels have the 2% of carbon. All steels having the carbon is there, and instead of carbon, iron is also there. So chromium steel, it is a alloy of chromium, then Fe and iron. This nickel steel, it is alloy of nickel, then iron, and then carbon. So carbon percentage is 2% in all these steels, nickel steel, chromium steel. These are all alloys of iron, in which the percentage of iron is more. Then I am coming to the non-ferrous alloys. In case of this non-ferrous alloys, these are alloys are formed with mixing atoms of transition metals other than iron. So iron is not included in this, remember. So in case of ferrous alloys, iron is there. In case of non-ferrous alloys, the iron is not there. Other than iron, other transition element, non-transition element is there. So we can see here one example is given: brass. Brass is an alloy of copper and zinc. Here copper is a transition element, but zinc it is not included in transition element, remember. So brass is an alloy of copper and zinc, remember. This question is asked for many times. Brass is an alloy of ... Bronze also, this bronze medal, you know, this bronze medal is given for the participants, gold medal, silver medal, and this bronze medal. So this bronze medal, it is alloy of copper and tin. Here copper is again transition element, but this tin is again the non-transition element. So ferrous alloys contains iron, and this non-ferrous alloys contain one transition metal and another one is non-transition metal, remember. Instead of iron, another non-transition metal is included in non-ferrous alloys. Then the uses of alloys, it is also very important for the examination purpose. They will ask, write the uses of bronze. So bronze, it is alloy of copper and tin. Already we learned here. Bronze, it is alloy of copper and tin. Copper and SN, it is very tough, strong. Corrosion resistance means it do not undergoes corrosion. So it is used for the making different statues, medals, trophies. Then cupra nickel, the name suggests it is an alloy of copper and nickel. Cupra nickel, it is used for making machinery parts of marine ships which are under the water. Marine ships, boats. For example, it is given marine condenser tube. This marine condenser tube, it is prepared by using this specific alloy. alloy of copper and nickel. Then stainless steel alloy, this is very famous alloy. I already explained this stainless steel. It is alloy of ferrous alloy in which the percentage of carbon is more. It is alloy of carbon, chromium, iron, chromium, and carbon. This stainless steel, you know, this is used for the kitchen accessories, then cutlery, also cookware. Then one important use is it is used for the construction of outer fuselage of ultra high speed aircraft. The fuselage means it is a what you can say entrance construction of exit construction of outer fuselage of ultra high speed aircraft. So for the preparation of this exit part of this ultra high speed aircraft, it is used generally it is used for the kitchen accessories. In kitchen we are using this stainless steel, all the cutleries, cookwares, it is made up with stainless steel. We are interested in this alloy only, Fe, chromium and its uses. Nichrome, as the name itself suggests, it is alloy of nickel and chrome. It is alloy of nickel and chrome. So it is a nickel and chromium is there. The ratio is 80-20, 80% of nickel and 20% of chromium. It is used for the it has been developed specifically for gas turbine engines. So for the preparation of gas turbine engines, this alloy is used. Then this titanium alloys are very hard. You know, this titanium is the main metal which can withstand the stress up to the high temperature. Then outstanding corrosion resistance used for ultra high speed flights. Then this fireproof bulkheads, it is used because these are very hard. Bulletproof, for the bulletproof glass, this titanium alloys are also used, remember, because it is very hard. This is a non-evaluative portion. This is deleted. The compounds of manganese, chromium, and chromium, manganese and chromium, this is deleted. This is also deleted. So this entire part is deleted, 8.7, remember. For the board examination. So all this part is deleted. Then I'm coming to this. Common properties of D block elements. So all the D block elements having these all are having the properties of metals. They show the properties of metals. Metals also having the luster, shining. Metals are hard. They having the high density. They having the high melting and boiling point. Good conductor of heat and electricity. They having the high tensile strength, malleability, ductility. They can form the alloys. They can use it as a catalyst. So these are the some physical properties of the D block elements, and these are not asked for the examination, remember. Then the chemical properties are also given. They are electropositive metals. Actually, they are having the properties in between S block and P block. S block elements are electropositive, then P block elements are electronegative. So they are having the intermediate properties of S block elements and P block elements, remember. They exhibit the variable valencies. Oxidation state are also valid. They form the colored salts compounds. They having the good reducing agent. They form insoluble oxides and hydroxide. They catalyze the biological reactions. Iron, cobalt, copper, molybdenum, zinc. These are biologically important metals. So these are some chemical properties. These are also not asked for the examination, remember. So the difference is most of the properties of D block elements are same. Elements of the first row. First row means it is a 3D series, scandium to zinc. So elements of the first row differ from the second and third row. in stabilization of higher oxidation state. One example is given, molybdenum plus 5 oxidation state, tungsten plus 6 oxidation state. These compounds are more stable. So these compounds are more stable than chromium plus 6 oxidation state and manganese plus 7 oxidation state. This is some differences are given. Most of the properties are same, only the differences are given, means which properties are different. So remember, they differ in stability. Elements of the first row differ from the second row and third row in stabilization of higher oxidation state. So molybdenum plus 5 oxidation state, tungsten plus 7 oxidation state, these compounds are more stable. See, though the oxidation states are less, these compounds are more stable than this is chromium and manganese. Chromium having the plus 6 oxidation state, manganese having the plus 7 oxidation state. Though the oxidation state of this chromium and manganese are higher, these molybdenum and tungsten, these are more stable. This is the difference of 3D series, 4D series and 5D series. Then another one example is also given. Higher oxidation states for the elements of the first row is plus 7. Manganese shows plus 7 oxidation state, and in the second and third row plus 8. This plus 8 oxidation state, it is shown in osmium tetroxide. Osmium tetroxide, osmium having the plus 8 oxidation state. Then this is a RuO4, in which this Ru metal, Ru, I think this is rubidium. Just I want to confirm this Ru. Ruthenium. So this ruthenium tetroxide, in the first transition series, this manganese shows plus 7 oxidation state, but in the second and third row, this osmium shows plus 8 oxidation state, and ruthium also shows plus 8 oxidation state. So don't take tension of these properties, because these properties are not asked for the examination. So I am going to stop here. I request all the students, please go through the alloys, catalytic properties, color. I completed the very important part today. Color having the question for the board examination, alloys also having the question for the board examination, and catalysts also having the questions on board examination. So I will stop here.